Today we're going to explore one of the most fascinating paradoxes in soft matter physics, the osmotic versus mechanical buckling paradox in microcapsules. First, let's understand what microcapsules are. Microcapsules are tiny spherical shells, typically ranging from 1 to 1,000 micrometers in diameter. They consist of a thin elastic shell enclosing an interior fluid, surrounded by an exterior fluid. The shell thickness is typically much smaller than the capsule radius. These structures are crucial in drug delivery, food technology, cosmetics, and advanced materials. Understanding their mechanical behavior is essential for designing robust capsules. Here's the paradox that puzzled scientists for years. When you apply the same amount of pressure to a microcapsule, you get completely different buckling shapes depending on how you apply that pressure. You might ask, why would the method of applying pressure matter if the net force on the shell is comparable? This is the heart of the paradox. Under mechanical compression, the capsule typically buckles into a shape with sharp creases and well-defined folds. External forces push directly on the shell. Under osmotic pressure, the same capsule buckles into a smoother, more oblate shape. Water molecules leave the interior, creating an indirect pressure through volume reduction. The resolution to this paradox lies in path dependence. The way the system reaches the final pressure state fundamentally affects the buckling outcome. Let's dive deeper into osmotic pressure. Osmotic pressure arises from differences in solute concentration across a semi-permeable membrane. The osmotic pressure pi equals the molar concentration C times the gas constant R times temperature T. This is the Van Hoff equation for dilute solutions. Here C is the solute concentration in moles per cubic meter. R is the universal gas constant, 8.314 joules per mole Kelvin. T is the absolute temperature in Kelvin. Let's calculate a typical biological osmotic pressure. Consider a concentration difference of 0.1 molar at room temperature of 298 Kelvin. The concentration is 0.1 molar, which equals 100 moles per cubic meter. Multiplying, we get pi equals 100 times 8.314 times 298, which equals approximately 248 kilopascals. That's about 2.5 atmospheres of pressure. This is substantial pressure generated purely from concentration differences. It's comparable to the pressure at 25 meters underwater. To understand buckling, we need to characterize the shell's elastic properties using the Föppl von Kármán number. The Föppl von Kármán number gamma equals yr squared divided by squared. This dimensionless number determines buckling behavior. Y represents the applied pressure or stress on the shell. R is the radius of the spherical shell. E is the Young's modulus, measuring the material's stiffness. H is the thickness of the shell wall. You might wonder, what does gamma tell us physically? It's the ratio of the shell's bending energy to its stretching energy. When gamma is large, bending deformations dominate over stretching. The shell buckles more easily with complex shapes. When gamma is small, stretching deformations dominate. The shell resists buckling and deforms uniformly. Now let's analyze mechanical buckling in detail. In mechanical compression, external forces act directly on the shell surface. Forces are applied uniformly from all directions. The shell experiences compression that's independent of the interior volume. Crucially, the shell deformation and the interior volume are mechanically decoupled. The shell can deform without necessarily changing the enclosed volume. The mechanical pressure difference equals the external pressure minus the internal pressure. The critical buckling pressure for a thin spherical shell under mechanical loading is given by a classic result. P critical mechanical equals 2E divided by the square root of 3 times 1 minus nu squared times h over r squared. Here nu is the Poisson ratio. Let's calculate for a typical polymer microcapsule. Consider a capsule with radius 100 micrometers, thickness 1 micrometer, Young's modulus 100 megapascals, and Poisson ratio 0.5. Radius is 100 micrometers, thickness is 1 micrometer. Young's modulus is 100 megapascals, Poisson ratio is 0.5. Substituting these values, we get P critical mechanical approximately equals 13 kilopascals. This is the pressure needed to buckle the shell mechanically. Osmotic buckling works completely differently. Here, the loading is intrinsically coupled to volume change. Water molecules leave the interior, driven by concentration gradients. As water exits, the interior volume must decrease, forcing the shell to deform. The key difference: shell deformation is tightly constrained by volume conservation. The shell cannot buckle without changing the enclosed volume. This coupling fundamentally changes the energy landscape of possible buckling modes. Different shapes become energetically favorable. Let's write down the relationship between volume change and osmotic pressure. The volume change delta 5 equals minus the initial volume, 5,0, times the integral of dp divided by pi of p. This shows the path-dependent nature of volume change. The integral here is crucial. It means the history of how pressure changes matters, not just the final pressure value. Let's analyze the energy to understand why different loading paths produce different shapes. The total energy equals bending energy plus stretching energy plus osmotic energy. For mechanical loading, the osmotic energy term is 0. Shell deformation and volume change are decoupled. For osmotic loading, the osmotic energy term couples shell shape directly to volume change. This additional constraint selects different equilibrium shapes. The osmotic energy equals the integral of pressure times volume change. This work term is path-dependent. The buckling mode is determined by which shape minimizes the total energy under the given constraints. Mechanical loading favors shapes with sharp folds and creases. This minimizes bending energy locally by concentrating deformation. Osmotic loading favors smooth, gradual deformations. This efficiently reduces volume while minimizing the energy penalty from the volume shape coupling. Here's a comparison. Mechanical buckling produces polygonal shapes with vertices and edges. Osmotic buckling produces smooth ellipsoidal shapes. Experiments beautifully confirm these theoretical predictions. Researchers have directly compared mechanical and osmotic buckling of identical capsules. One method uses micropipette aspiration to apply mechanical pressure. The other uses osmotic shock by changing external solute concentration. The results are striking. The same capsule buckles into distinctly different shapes depending on the loading method, even at the same pressure. An interesting question: can we reverse the buckling by reversing the pressure? The answer depends on whether the deformation is elastic or plastic. For elastic shells, the buckling is reversible. However, the path still matters for the dynamics of shape recovery. The buckling transition itself exhibits interesting critical behavior. There's a well-defined critical pressure at which buckling occurs. Remarkably, the critical osmotic pressure difference is typically less than the critical mechanical pressure. Osmotic loading can buckle shells more easily. Why? The volume constraint actually makes buckling easier in some cases because it provides an additional degree of freedom for energy minimization. A complete description requires nonlinear elasticity theory. The shell undergoes large deformations where linear theory breaks down. The strain tensor epsilon includes nonlinear terms. This is the Green-Lagrange strain tensor for finite deformations. The nonlinear terms become crucial when the thickness to radius ratio is small, which is exactly the regime of thin microcapsules. This paradox has profound implications for practical applications of microcapsules. In drug delivery, the release mechanism can depend on whether the capsule experiences mechanical or osmotic stress. Different stresses produce different rupture patterns. In industrial processing, capsules may experience mechanical handling or osmotic conditions. Understanding both is essential for preventing premature rupture. A key design principle: you can control the final shape by controlling the loading path, even at the same final pressure. Here's an analogy to help understand path dependence. Imagine climbing a mountain. You can reach the same summit, representing the final pressure, by taking completely different routes up the mountain, representing different loading paths. Each route crosses different terrain. Similarly, each loading path explores different regions of the energy landscape. You arrive at the summit tired in different ways depending on your route. Similarly, the capsule reaches the final pressure in different shapes depending on the loading path. Let's quantify the shape difference using aspect ratios of the buckled capsules. For mechanical buckling, the aspect ratio AR mechanical equals the maximum dimension divided by minimum dimension, typically ranging from 3 to 5. For osmotic buckling, the aspect ratio is typically smaller, ranging from 1.5 to 2. The shape is less extreme. This quantifies what we see. The osmotic shape is more symmetric and gentle compared to the sharp mechanical buckling. The dynamics of buckling also differ dramatically between the two mechanisms. The mechanical buckling time T mechanical scales as eta R divided by EH squared times L squared, where eta is viscosity and L is a length scale. The osmotic buckling time T osmotic scales as R squared divided by D, where D is the water permeability coefficient. Typical mechanical buckling happens in milliseconds to seconds. It's relatively fast. Typical osmotic buckling takes seconds to hours. It's much slower because it's limited by water transport. What happens when both mechanical and osmotic stresses are present simultaneously? This intermediate regime is particularly complex. There's a competition between the two mechanisms. Which one dominates depends on their relative magnitudes and timescales. We can define a dimensionless parameter lambda as the ratio of mechanical to osmotic pressure. When lambda is much greater than 1, mechanical effects dominate, and we see mechanical type buckling. When lambda is much less than 1, osmotic effects dominate, and we see osmotic type buckling. When lambda is approximately 1, we can get complex hybrid shapes that exhibit features of both buckling types. Recent research has uncovered even more subtle aspects of this paradox. One discovery is that buckling can be bistable. Multiple stable states can exist at the same pressure. This leads to shape memory effects, where the equilibrium shape depends on the loading history. Fascinatingly, you can switch between these states with small perturbations, opening possibilities for controlled shape changes. Let's write down the complete mathematical framework using free energy minimization. The free energy F involves an integral over the shell surface of elastic energy terms minus pressure times volume change.Cijkl is the elasticity tensor, and kappa is the bending rigidity. We minimize this free energy with respect to the displacement field U to find equilibrium shapes. The key is that the constraints differ. Mechanical loading fixes pressure. Osmotic loading fixes the rate of volume loss. Red blood cells provide a beautiful real-world example of this physics in action. Red blood cells have a characteristic biconcave shape. This shape results from osmotic pressure balance. When red blood cells are subjected to mechanical stress, like in blood flow, they deform differently than when subjected to osmotic stress from salt concentration changes. This shape response affects oxygen transport efficiency and cell survival. It's crucial for their biological function. Modern computational studies use finite element analysis to simulate these buckling processes in detail. These models capture the full nonlinear mechanics of shell deformation, including large deflections and material nonlinearity. They can predict exact buckling shapes and transition pressures with remarkable accuracy. When compared to experiments, these simulations show excellent agreement, validating our theoretical understanding. Despite significant progress, several open questions remain. First question: how do defects in the shell affect the path dependence? Real capsules are never perfect. Second question: can we exploit this paradox to design smart materials that respond differently to different stimuli? Third question: what happens in non-spherical geometries? Most theory focuses on spheres, but many applications involve other shapes. Let me summarize some practical design guidelines based on this understanding. First, predict whether your application involves primarily mechanical or osmotic loading. Second, design the shell thickness to achieve the desired critical buckling pressure for your loading type. Third, consider the time scales involved. Fast processes favor mechanical, slow processes may be osmotic. Fourth, always test under realistic conditions that match your application, because lab conditions may not replicate the actual loading path. Let me summarize the core physics of this fascinating paradox. Key point 1. The same final pressure can produce completely different buckling shapes, depending on how that pressure is applied. Key point 2. This path dependence arises because osmotic loading couples shell elasticity to volume change in a fundamental way. Key point 3. The energy landscapes explored during buckling differ between mechanical and osmotic mechanisms. Key point 4. Practical applications must carefully consider the type of loading their capsules will experience. This paradox beautifully illustrates the richness of soft matter physics. A seemingly simple system, a spherical shell under pressure, reveals deep principles about path dependence and constraint-driven mechanics. Theory and experiment work together perfectly here, each illuminating the other. The practical impact spans from medicine to materials science, affecting how we design everything from drug delivery systems to protective coatings. Understanding the coupling between geometry and loading is essential for predicting and controlling the mechanical behavior of complex systems.